Hi, welcome to the next lecture in the NPTEL course Machine Learning for Core Engineering Disciplines. In the last time we looked at principal component analysis as one of the simplest algorithms for unsupervised learning. We learned that it is a dimensionality reduction technique and essentially involves determining the eigenvectors and the eigenvalues of the covariance matrix after you have zeroed out the means of each feature and you have made the variance of each feature equal to 1 by normalization. We also discussed that the largest eigenvalue, the eigenvector corresponding to that is the first principal component, and so on and so forth. You can determine all the principal components, and the main advantage of that is you can reduce the number of features by combining them into the principal components. So, you can train simpler models, avoid overfitting and get more physical insight by visualizing data in the space of the principal components. Now, in today's lecture we will delve a little bit deeper into the foundations of principal component analysis through a technique known in linear algebra and matrices as singular value decomposition. So, let us go ahead and understand singular value decomposition, and once we finish it we will start discussing other kinds of algorithms such as clustering, which are also available for unsupervised learning. Okay, so the topic for today is singular value decomposition. And how it ties into principal component analysis. Which is PCA. Alright, so how does this work and what exactly is meant by a singular value, right? That is what we will try to understand here. So, SVD or singular value decomposition, that is basically the extension. So, SVD is the extension of the concept of eigenvalue decomposition which is only applicable to square matrices. To rectangular matrices. Which are encountered frequently in ML. Okay. So, if you remember, we usually denote the data matrix as X. So, X is the data matrix and it is usually of the size n by p, where n is the number of data points and p is the number of features. Now, rarely, right, if at all ever would n be equal to p, right. So, for this particular matrix X matrix to be square, n should be equal to p, but obviously in ML the number of data points is usually much larger than the number of features. So, then you do not have a square matrix. So, the concept of eigenvalue decomposition which is only applicable to square matrices cannot be applied here. So, we are working with the rectangular matrices instead, right, because n is not equal to p, and therefore we need a different concept which is essentially singular value decomposition. So, let us go ahead and understand what this means. So, if you recall what is eigenvalue decomposition, right. Essentially you can write a square matrix, right, A, which is a square matrix, can be written as the product of 3 matrices Q lambda Q inverse, okay. And here Q is the matrix of eigenvectors. So, matrix formed by the eigenvectors of A, and this lambda is a diagonal matrix of eigenvalues, right. Basically eigenvalues are on the diagonal, and we have already seen this eigenvalue decomposition in some of the earlier lectures when we also studied the Hessian of a matrix and the positive definite and positive semi definite nature of Hessians in certain specific cases. Now it is good to know that this is also called eigen decomposition or matrix diagonalization. Right, because this lambda, which is the matrix of eigenvalues, is essentially a diagonal matrix, right. So, this is something you already know. You also know what is meant by the eigenvalues. So, the eigenvalues are defined using this equation AV equal to lambda V, right. So, these V's are called the eigenvectors and lambdas are called the eigenvalues. And of course, A is a square matrix. So, it is of size, let us say m by m, right. So, it is a square matrix. Okay. Now, there are certain specific requirements for eigen decomposition to exist, and also under certain specific cases you can say something more about this matrix Q, which is the matrix of eigenvectors. So, let us go ahead and look at some of these specific scenarios. So, there are some notes, right. The first is that, and this is something you already seen, for a real symmetric matrix, and an example is the Hessian that you encountered a few lectures ago, right. For such symmetric matrices which are real, Q inverse is essentially Q transpose, right. That is, Q is an orthogonal matrix, and then you can write A basically as Q lambda Q transpose, right. So, this can be written. The second important point to note is that for eigen decomposition to be possible, Q inverse must exist, right, and thus the eigenvectors must be linearly independent. Right, essentially your Q matrix cannot be singular, and one could also say that the eigenvalues have to be distinct, right. So, now what happens if either Q inverse does not exist or Q is not a A is not a square matrix, right. So, then what do we do, right. So, that is where singular value decomposition comes into the picture. So, now if Q inverse does not exist or A is a rectangular matrix, eigenvalue decomposition is not possible, but one can define the singular value decomposition. and essentially this is important for the data matrix X in machine learning, because X is a rectangular matrix, right. So, if you are talking about a rectangular matrix like X, right, X which is usually of size n by p, number of data points is the number of rows and number of features is the number of columns. So, for such matrices the matrix, right, X can be written as the product of 3 matrices, right. So, just like there were 3 matrices here, q lambda q inverse or q lambda q transpose, right, for a real symmetric matrix, here for any rectangular matrix you can write it as the product of 3 matrices, and I will define these matrices now. The first is a so called unitary matrix, a unitary matrix U of size n by n whose inverse equals its Hermitian transpose. So, essentially U inverse is equal to the Hermitian transpose of U, and you know that the Hermitian transpose is basically the complex conjugate transpose of the matrix, right. You take the complex conjugate of every entry and then you take the transpose. Okay. So, this is the U matrix. Then a diagonal matrix denoted as uppercase sigma of size n by p, and another unitary matrix which is denoted as V Hermitian transpose of size p by p. Okay. So, essentially X is equal to U sigma V Hermitian transpose, and you can see that the dimensions of the matrices work out, right, because U is of the size n by n, sigma is of the size n by p, and V Hermitian is of the size p by p, right. So, for the first matrix multiplication to define, this n and this n they are equal, and for the second matrix multiplication to be defined, this p and this p are equal. So, finally the size of the matrix that will come out will be of size n by p, which is the size of X. So, whatever we have written is consistent in terms of the sizes of the matrices, right. Now, this is of course a mathematical statement, but it is often useful to think about what is going on behind the math, right, what is the physical intuition or physical meaning. So, let us look at that. So, essentially any matrix is a linear operator, right, since you can operate it on a vector to get another vector. So, X, right, which is of size n by p can be thought of as a linear operator. Since if you take X, right, of size n by p, and let us say you operate it on V which is of size p by 1, you get another vector of size n by 1. So, it is a transformation, it transforms the vector V into the vector U. So, that is why it is a linear operator, okay, where V is a feature vector of size p by 1 is mapped to the sample space, right. You know that there are n data points. So, this is some sort of a mapping to the sample space. Okay. So, essentially we are saying that there are 3 matrices and there is a physical operation that would correspond to each of these 3, right. So, these are the 3 matrices, right. So, this linear operator X we are splitting into 3 matrices U, sigma and V Hermitian, and these are the 3 operations, right. So, we are decomposing X into 3 linear operators, and this is a rotation. So, when you operate X on V, first that V will be operated by VH, then it will be operated by sigma, and then it will be operated by U, right, because matrices always work right to left. So, first you are doing a rotation which is represented by the matrix V Hermitian transpose, then you do stretching, right, using the diagonal matrix sigma, and then you have another rotation. Right, and this is how it helps you to find the directions in which the variance is maximum, right. If you remember, that was the physical interpretation of principal component analysis. It tells you the directions along which the variance is maximum. Okay. So, how does this happen, right. So, let us draw an illustration, right. So, let us say you have some data here, right, which is appearing like this, right, it is distributed like this, and then these are 2 axes right here, and you are applying this linear operator X, and then you are getting a different sort of data that is distributed in a slightly different way, and let us say these are the axes. So, what we are now saying is that this is a combination of 3 operations, VH which is rotation, right, and then there is stretching which is sigma, and then we need to do another rotation. So, essentially this could look something like this, right. So, once you rotate, the data is basically rotated, right, and yeah, let us use slightly different colors here, right. So, the data is rotated. So, let us say these axes now look like this. Then after rotation you have stretching, right. So, the data has been stretched, right, and these are the 2 vectors that we were monitoring, and then finally this is again slightly rotated here, right. So, you can see that is the physical interpretation of singular value decomposition, and that is how you are aligning it along the direction in which there is maximal variance, right. So, that is the link between SVD and PCA. So, that is more intuitive, but what about the mathematics, right, and what exactly is a singular value. So, let us look at that now. So, a singular value is the extension of an eigenvalue to a rectangular matrix. So, if you remember, we define an eigenvalue for a square matrix which is AV equal to lambda V. In a similar manner, we define a singular value for a rectangular matrix. So, a singular value sigma is defined as by these equations. So, if you take X and operate it on a vector V, and mind you now X is a rectangular matrix, you get sigma times U. So, this is lowercase sigma, and then if you take X Hermitian and operate it on U, you get sigma times V, right. So, here V and U are the extensions of the concept of an eigenvector, right, which was defined for a square matrix. So, now we are defining singular values for a rectangular matrix. So, here V and U are called right and left singular vectors. respectively. Okay. So, now something interesting will emerge, right. So, let us call this equation 1, let us call this equation 2. If you now multiply the first equation by the Hermitian transpose of x, let us see what happens. You get x Hermitian times xv is equal to x Hermitian sigma v, right. And now you know that this is essentially sigma times, sorry, the first equation had u here, right. So, this is sigma u, and now you can rearrange this slightly. So, this becomes sigma times x Hermitian u, and you know that from the second equation, right, x Hermitian u is sigma v. So, this is sigma times sigma v from equation 2, and therefore, now you have sigma squared v. So, x Hermitian x times v is equal to sigma squared v. Okay. Now, this is very interesting. Why is it very interesting? Because you can compare this equation to the equation used to define an eigenvalue, and immediately you see that v is the eigenvector of x Hermitian times x, and sigma squared is the eigenvalue of x Hermitian x, right. So, it is fascinating. We have demonstrated a link between singular value decomposition and eigen decomposition, right. So, singular value decomposition of x is equivalent to the eigen decomposition of x Hermitian x. And if you go back and remember what happens in PCA, we are doing eigen decomposition of x transpose x. Now, if x is a real matrix, then x Hermitian transpose and x pure transpose are one and the same thing. So, I hope you are seeing where I am getting to. Okay. So, let us write whatever I just said in words to fructify the concepts. So, essentially sigma squared, which is the singular value squared of x are the eigenvalues of x Hermitian x, and singular vectors of x are eigenvectors of x Hermitian x. Okay. Now, let us consider real data. So, considering x to be real, what happens, right. So, we can write that SVD of x is equivalent to eigen decomposition of x transpose x, and this you know is essentially principal component analysis. So, thus we have demonstrated a link between singular value decomposition of the data matrix, eigen decomposition of the covariance matrix. Remember, this is n minus 1 times the covariance matrix, with standardized data. I told you that standardization means you zero the mean and you make the variance as 1, right. So, this X transpose X is essentially the covariance matrix without a constant factor, and that is essentially principal component analysis, because only the directions matter, right, of the principal component. Once you know the directions, you can always normalize them. Alright, so I hope this clarifies the link between singular value decomposition of the data matrix X, the eigen decomposition of the covariance matrix, and the concept of principal component analysis, which tells you the direction in which one should essentially move to see the maximal variance. Alright, so before ending the lecture, I want to cover one last concept, and this is again very important from a practical standpoint, and the question I want to answer is, how does one choose how many principal components to use, right. So, you know that you will get many principal components and you will have to choose, right, some of them. So, this is decided via something known as a Scree plot, right, and I will show you what this plot means now. So, essentially you are plotting on the y axis the eigenvalues of the covariance matrix. Of the data. Okay, so that is what is there in the y axis, and on the x axis you just plot the principal component number, right. So, you know that the first principal component corresponds to the largest eigenvalue, right. So, obviously that point will be somewhere here. So, let us say this is the first principal component, then you may look at the second principal component, and the second principal component corresponds to the second highest eigenvalue. So, then perhaps that is here, then you go to the third principal component, and further there is some reduction. So, let us try to make this a bit more clear. So, there is a lot of reduction, then there is more reduction, and so on and so forth. So, if you keep on plotting, let us say it falls like this. Okay. Now, what you can do is you can try to find out where the drop in the eigenvalues levels off, right. So, if you look at these 2 points, this is where the eigenvalues have leveled off, right, and these principal components are where there is significant kind of reduction, and you can see that more and more variance is being captured. So, these PCs capture a significant amount of variance and should be chosen. Okay. And this is how you determine how many eigenvalues, right, and how many principal components to use in principal component analysis. So, you do not have to use all the principal components, you can only use a subset of them, and that is the entire point, right. You want to do dimensionality reduction, you want to reduce the number of features, right, that you are working with, and one point of course is that these principal components, you know, they are in increasing order, right, these are in decreasing order of eigenvalues, right. So, that brings me to the end of this particular lecture. Today we discussed the mathematical foundations of principal component analysis in terms of singular value decomposition. We learned that SVD is essentially the extension of eigenvalue decomposition to rectangular matrices. That is very important for ML because rectangular matrices is all what we work with in ML. The number of data points is hardly ever equal to the number of features. Usually it is much more than the number of features to find all the hidden insights that ML has to offer. Then we saw that PCA is essentially eigen decomposition of the covariance matrix, and that is the same as the SVD of the data matrix X. And towards the end of the lecture we also discussed how we can use a Scree plot by plotting the eigenvalues of your covariance matrix to determine how many principal components to use in terms of when the eigenvalues level off and you do not really get any more value out of increasing the number of principal components. I hope you found this lecture useful, and thanks for joining. I look forward to seeing you next time.